Hey folks, I'm going to be covering the last handful of objectives of the curriculum with you through these amazing edited videos that have some notes, some practice problems on the last part of Unit 9. So we covered the first part of Unit 9 back in Unit 6 when we did thermodynamics, and we talked about Gibbs free energy and how that relates to delta H and delta S. And now we're looping back and talking about delta G Gibbs free energy again under the umbrella of equilibrium, and also we will be applying this to electrochemistry. So this section 9.5 is about free energy and equilibrium. There is a mathematical relationship. You are given an equation on your sheet. So we can look at the relationship between delta G and K, the equilibrium constant of a process, to determine how favorable something is. So we've already talked about how negative delta G is a favorable forward process. So we can also look at assumptions of how a value of K can be related to that. So the objective 9.5 is you'll be able to explain whether a process is thermodynamically favored using relationships between K, delta G, and temperature. And we've already talked about a negative delta G. And if products are favored at equilibrium, that means K is greater than 1, because when we are dealing with reactants and products, our equilibrium constant is determined by the concentration of products over reactants. So a forward reaction, which is favorable with a negative delta G, means we have a lot of products. So a high amount of products, a lower amount of reactants, gives us a K value greater than 1. This equation, that's floating around. This equation is on your reference sheet. So we've calculated delta G in different ways already. We've calculated delta G as the summation. We've calculated delta G equal to delta H minus T delta S. And we've also calculated delta G using Hess's law, which we're going to revisit as well. So this is the third way that we are going, or fourth, I guess, way that we're going to be calculating delta G. And then this just kind of summarizes our things as well. Okay. So we already know that thermodynamically favored means products are favored at equilibrium. And at equilibrium, there's no overall change in concentrations. Free energy and equilibrium constant have this mathematical relationship that I have here highlighted in yellow. We can rearrange this equation to solve for K if we take and divide out this negative RT. So we have like negative delta G over RT equals the natural log of K. If I want to get K by itself, the way that I undo a natural log is with that lowercase e button on our calculator. And do I remember what that really means? No, but what do? We push the buttons. That's where this comes from. So you're given this equation that I have highlighted in yellow, but if you're given like delta G and the temperature, you can solve for K by rearranging it. And you need to know how to solve that algebraically on your calculator. Qualitatively through estimation here. So this is like a prediction sort of thing, that if you aren't given the actual numbers, you can make a prediction here. If I have a negative delta G, I can assume that it's moving forward. And if it's moving forward, I have lots of products. K is greater than 1. We have a lot of product. And then the opposite here. This last part is important here. When delta G is equal to 0, the reaction is at equilibrium. We have solved questions like that with our prior equation. At what temperature does this process become favorable? We set delta G equal to 0. That's when it's at equilibrium and both processes are occurring. Let me go over here. So this just kind of repeats, repeat. Now, this is also important. When we're using this calculation, whatever we're solving for, we have R in here. R is a gas constant. We have used R before in PV equals nRT. And the value that we chose to use for R from our reference sheet was dependent upon what unit of pressure was being used in our question. There is another value for R that involves joules. Hey, that's a form of energy. Oh my gosh, Gibbs free energy. So when you are using this delta G calculation that involves the gas constant, you must use 8.314. You also need to know that temperature must be in Kelvin, because the unit of temperature in our gas constant is in Kelvin. All right, so let's look at this example multiple choice question. So we're given this equilibrium system. We have two aqueous ions coming together, adorable. At 25 degrees Celsius, the equilibrium constant for the reaction represented above has a value of 1.3. At 50 degrees Celsius, the value of the equilibrium constant is less than 1.3. Based on this information, which of the following must be correct? So we have all these options here. Okay, so let's kind of weed our way through our answer choices. So choice A, the reaction rate decreases as the temperature is increased. That is not going to be true because kinetics tells us that an increase in temperature increases the frequency of collisions, therefore increasing reaction rates. For choice B, the reaction is thermodynamically favorable only at temperatures above 25 degrees Celsius. So let's look at what we're given here. We're told that at 25 degrees Celsius, the equilibrium constant is equal to 1.3. Well, an equilibrium constant greater than 1 tells us that we have product present because that equilibrium expression for this equation would be products over reactants. So if this is equal to 1.3, then we know we have product being made. So we know this process is thermodynamically favorable at 25 degrees Celsius. So we can also infer that delta G is less than 0 if it is thermodynamically favorable. So that eliminates choice B. For choice C, at 25 degrees Celsius, the delta G for the reaction is positive. That would be unfavorable, which we already determined is not going to be true because we have a K value greater than 1. Choice D, at 25 degrees Celsius, the delta S for the reaction is positive. So remember, delta S is our change in entropy, and a positive change in entropy means greater disorder as we're moving through the process. So looking at this reaction, we go from two aqueous ions to a single aqueous ion. So we are decreasing in entropy, which means we would have a negative delta S, which makes this not true either. So that gives us choice E. But I want to look at why choice E works. Let me erase some of these markings. Okay. At 25 degrees Celsius, delta H for the reaction is negative. So that means it's this is saying an exothermic process. So that means I'm going to put the heat on the right-hand side. Let's look at a couple things here. We are told in the prompt that when the temperature jumps from 25 degrees Celsius to 50 degrees Celsius, my K value drops. Okay? We know from equilibrium, our equilibrium unit is that the only thing that can change the value for K is changing the temperature of the system. So we've got that. That is a possibility. The K is changing here. So if K is decreasing as the temperature rises, if K is decreasing as the temperature goes up, that means the process is becoming less favorable as the temperature goes up. Because decreasing K, looking back at this ratio here, if I want my value for K to go down, I need my amount of product to go down and my amount of reactant to go up. So if that is occurring, my amount of product is decreasing and my amount of reactant is increasing, that means that increasing the temperature shifts my reaction in the reverse direction. It was at equilibrium and now it has shifted. Okay? So if increasing the temperature causes my reaction to shift in the reverse direction, when we increase the temperature, the endothermic direction is favored. So that means, looking at this answer choice now, at 25 degrees Celsius, the delta H for the reaction is negative. If I have a negative delta H, I'm going to put it on the right side of the equation, which is what I have done here. Okay, there's a lot of thinking through that question. The couple of the answer choices, like B and C, are related. So if you understand one of those, then you'd be good for both of those choices. And then for choice D, we've already talked about that. And choice A has to do back with kinetics. This question here, using principles of thermodynamics to answer, the gas N2O4 decomposes to form NO2. So there's two NO2s according to this equation. Predict the sign for delta H and justify your answer. Predict the sign for delta S and justify your answer. So for the first part, when I was looking at this question at first, I was like, wait, what? Let's think about it. We're taking a molecule and we are breaking it apart. We're breaking this bond to form these two molecules as a result. Okay, so if we're breaking a bond, we remember everyone's favorite acronym, BARF. Breaking a bond requires absorbing energy. Absorbing energy is an endothermic process. The sign of an endothermic process would be positive. Okay, so this is a bonding type of question. So that's a positive delta H. And you can justify the answer by saying a bond is being broken to separate the N2O4 molecule into two NO2 molecules. Breaking bonds is always endothermic. Done. Predict the sign of delta S for the reaction and justify your answer. So delta S is based on entropy. So I'm going from a single gaseous reactant to multiple gaseous products. So that's going to be a positive change in entropy, and justifying it is just what I said before. Now, for this process, it's saying the gas decomposes. So this reaction is happening. So if it's happening, that means it happens to be thermodynamically favorable at whatever temperature they're dealing with. So that means, thinking back to what our sign situation was, a positive delta H is not favorable. A positive delta S is favorable. So when I have those two signs in conflict with each other, with the entropy being the favorable one, and we're being told the process happens, then we would say that it's under the control, if it's an entropy-driven process, if it does in fact happen at a particular temperature. There's follow-up here. Reaction mixture is at equilibrium. So I have both of these things in the same container. It's at equilibrium. So we have conversions occurring. Heat is added to the mixture while it's maintained at constant pressure. So we have already said that the forward reaction, it has a positive delta H. So the forward reaction is endothermic. So I'm just going to write heat over here on the left-hand side. Heat is added to the mixture while it's maintained at constant pressure. So that means we have a container with a movable piston. It can expand. Explain why the concentration of N2O4 decreases. So if we've established from earlier that this is an endothermic process in the forward direction, heating it up drives that endothermic process further. So in terms of like Le Chatelier's principle and shifting, that's going to favor the forward reaction. The forward reaction results in a decrease in the concentration of the N2O4 reactant. So explain why the concentration decreases. Increasing temperature favors the endothermic reaction, which would cause N2O4 to decompose, and that would decrease its concentration. The second part, the value of the equilibrium constant at 25 degrees Celsius is 5 times 10 to the negative third. Will this value be greater than, less than, or equal to, at 100 degrees, will it be greater than, less than, or equal to this value? So if we change the temperature, we know that we can change the equilibrium constant. So let's go back here. If we increase the temperature, we are driving this forward reaction, which means we are increasing the amount of NO2, which is product. We are decreasing the amount of N2O4. What does that do to our equilibrium ratios? Because we have the NO2, and that's going to be squared because there's two of them in the product side. And we have this N2O4. So if we drive this reaction forward and increase our numerator and decrease our denominator, that will make our K value greater than the initial K value we were given. Now, here's another question that's not on here. What would happen to delta G at this higher temperature? Well, if I'm driving it forward and making more product, that's a more favorable forward reaction. What would happen to the numerical value for G? It would decrease. It would get more negative because a more negative value means more favorability. I can get a number off of that, negative RT, natural log of K. If I solved for K, I can get my new delta G value. And this is mentioned back here. The natural log of a number that's greater than 1 will be positive. The natural log of a number that's less than 1 will be negative. So I can keep driving this reaction forward. This last slide just gives you a summary. We've talked about thermodynamic favorability. Now we're looking at that relationship. I'm going to show you a couple problems solved on the I do, we do, you do sheet.